Hello, night owls and curious minds. Tonight we're diving deep into the fascinating world of materials science, exploring how cutting-edge research is transforming our understanding of materials at the atomic level. We'll be unraveling the mysteries of something called electronic descriptors and how they dictate the properties of metal surfaces. Our guest tonight is Adeline, a leading expert in this field. Adeline, welcome to the show.
Thanks for having me, Adam. It's great to be here.
So, Adeline, let's tackle this head-on. Predicting the behavior of electrons in materials is notoriously difficult, right? I mean, we're talking about incredibly tiny particles interacting in incredibly complex ways.
Absolutely, Adam. Traditional methods for predicting electronic structure, while powerful, hit a wall when you try to scale up to larger and more complex systems. The computational cost becomes astronomical, and analyzing the results to get real insights is a significant hurdle.
And that's where this remarkable research comes in. We're talking about the work of Huang, Shihan Wang, Mohit Kamanuru, Luke E. K. Ashenyi, John R. Kitchen, and Hongliang Xin, published in Physical Review B. Their paper, Unifying Theory of Electronic Descriptors of Metal Surfaces upon Perturbation, offers a new approach. Adeline, can you explain their groundbreaking approach?
Certainly. Their key innovation is combining the power of machine learning with our established understanding of the underlying physical processes. They created a model that's not just accurate in predicting how the electronic structure of a metal surface changes when you alter it, say, by adding another metal or applying strain, but also explains why those changes occur. They've essentially built a bridge between the data-driven world of artificial intelligence and the physics-based world of materials science.
That's fascinating. So what are some of these key factors that influence these electronic descriptors of metal surfaces?
Well, they identified 4 major players: charge transfer, strain effects, ligand effects, and a newly discovered factor they call orbital resonance. Charge transfer is about how electrons redistribute themselves when different elements are brought together. Strain effects are about how stretching or compressing the material structure affects the electrons. And ligand effects involve the influence of neighboring atoms on the electron distribution of a given atom. Finally, the orbital resonance effect is a new contribution showing how the alignment of electron orbitals between different atoms influences the shape of the energy distribution.
Imagine that. It's like a complex dance of electrons influenced by their surroundings. How does this research improve our ability to design new materials?
This approach allows scientists to predict the electronic properties of a material with high accuracy and understand the underlying reasons for those properties, leading to a more efficient design process. Instead of relying on costly and time-consuming trial and error methods, researchers can now use this model to fine-tune materials' properties for specific applications, for instance in heterogeneous catalysis.
Adeline, this has been incredibly insightful. Thank you for sharing this groundbreaking work with our listeners. For those who are curious, the complete study is accessible at the link mentioned earlier in the show.
My pleasure, Adam. It's an exciting time for materials science, and I hope this conversation has sparked some curiosity about this important research.
And that's all the time we have for tonight, listeners. Join us next time for another fascinating exploration into the world of science and technology. Until then, keep looking up.